Hello everyone. In this video, we are going to look at the examples of solution to Laplace equation for one-dimensional potential function. We know Laplace equation is applicable for a charge-free region. Here, if the charge-free region is considered, its volume charge density is 0 and thereby del square V equals to 0. This becomes the Laplace equation. Let us take the example of parallel plate capacitor. We have two parallel plates of the capacitor. In this case, it is oriented perpendicular to x-axis. The region between the two plates is filled with an insulating material with the dielectric constant epsilon r, which decides the permittivity of the region as epsilon naught times this epsilon r value. And here we consider the distance of separation between the plates is d. We try to find the potential function V between the two plates of this capacitor. When we consider the region between the two plates of the capacitor, there is no free charges contained in this region. So thereby, if the region between the two plates is charge-free, we can apply this Laplace equation for this charge-free region to get the potential function V. We know potential from one plate to another plate varies through the axis x. Here it is a function of only variable x. That is why we call this as the one-dimensional potential function. We know the potential is a function of only one dimension, which is x. We will solve for the potential function of x taking this Laplace equation. And we should consider for solving the second order differential equation, two boundary conditions are required. One is the condition at the boundary between the first plate and the dielectric material, and the second is the condition at the boundary between the dielectric and the second plate. So for the first plate, we can consider the value of x is 0, and for the second plate, the value of x is d. Since we consider d is the distance of separation between the two plates, we will have to identify the boundary conditions and apply for this Laplace equation to solve for the potential function V. After getting this potential function V, we can find electric field intensity as negative gradient of potential. And we know flux density D can be written as epsilon times E vector. And from this flux density, we can find the charge as surface integration D dot ds from Gauss law. And once we know the charge stored in either of the plates of the capacitor, we can get the capacitance as charge stored in either of the plates divided by the potential difference between the two plates. So these are the steps to get the capacitance by solving the Laplace equation. Let us look at this case of parallel plate capacitor and obtain this V function and obtain subsequently all these things to get the capacitance expression for this parallel plate capacitor. So let us consider the Laplace equation, which is del square V equals to 0. And we know the configuration of the capacitor where the distance of separation is d and cross-sectional area or the area of each of the plates of the capacitor is S. The medium separating the two capacitor plates is filled with the dielectric constant epsilon r. And we can write the boundary conditions now by providing this capacitor some supply voltage. We will understand how the potential is going to be there between the two plates of the capacitor. If I connect V0 power supply to the plates of this capacitor, one end is grounded where the negative terminal of the supply potential is grounded and also connected to this plate where x is 0. And at the plate where x is equal to d, we are providing a positive potential V0. From this, we can write the two boundary conditions. That is, at the plate x equal to 0, potential is 0 since it is grounded. And at the plate x equals to d, the potential is plus V0. Now, these two forms the two boundary conditions required to solve for the second order differential equation from Laplace equation. We can write the Laplace equation in rectangular system of coordinates because we are taking the axis x, which is one of the axes of rectangular system of coordinates. So del square V function for rectangular system of coordinates can be written as second order partial differentiation of V with respect to x plus second order partial differentiation of V with respect to y plus second order partial differentiation of V with respect to z equals to 0. Since the region between the two plates is charge free, we can write the rho v value as 0 and thereby this is the Laplace equation. We know the potential difference between the two plates or the region between the two plates is a function of only x variable. Thereby, when we consider the differentiation with respect to y and z will be 0 because v is a function of only one dimension x, and thereby the differentiation of v with respect to y and differentiation of v with respect to z becomes 0. We have only this differentiation, which is the second order differentiation of v with respect to x. Since v is only a function of x, instead of partial differentiation, we can write the ordinary differentiation equation, which is the second order differential equation, d square v by dx square equals to 0. Now, to find v, we need to perform integration of this twice. Since this is the second order differentiation, 2 times we have to integrate and find what is the potential function v. The first time integrating this equation with respect to x will give the left hand side, we are doing one time differentiation integration with respect to x, and in the right hand side 0 is integrated with respect to x. So by doing first integration, one order of differentiation will be cancelled. We will be getting in the left hand side dv by dx, and integration of 0 is 0. Since we don't have the limits of integration, we have to write integration constant c1. Now this has to be again integrated to get v. So second time integration with respect to x for the left hand side and right hand side we should do. For the left hand side, integration of dv by dx with respect to x, and in the right hand side, integration of this constant c1 with respect to x we have to perform. So that is going to give in the left hand side v, and integration of c1 dx will be c1x. Since we don't have the limits, we have to write the integration constant, which is c2. So this is the function v with two constants c1 and c2. We need to find these constants c1 and c2 by applying this boundary conditions. So this constant c1 and c2 can be found by applying the two boundary conditions. Here we have the two boundary conditions. When we apply the first boundary condition, which gives at x0, v is 0. Thereby, if you substitute x0 and v0, you will get c2 becoming 0. By applying the second boundary condition, which is at x equal to d, v is v0. By applying that, we will get v0 equals to c1 into d plus c2. We already know c2 is 0. This can be removed. Thereby, we will get the constant c1 as v0 by d. Applying this constant c1 and c2 into this expression, we will get the potential function v. Thereby, we get c1 is v0 by d into x and c2 is 0. That is going to give the potential function which has only variable x. So we can write v as a function of only x equal to v0 by d into x, and the unit for potential function is v. We have got first the solution of potential function from the Laplace equation taking the two boundary conditions for the parallel plate capacitor. Next step, we can estimate the electric field intensity in the region between the two plates, which can be estimated as negative gradient of potential. We can write the gradient formula in rectangular system, and we can perform differentiation of this v function with respect to x, with respect to y, and with respect to z to get the electric field intensity in vector form. So take this differentiation of this with respect to x. We will get x term is present, so we will get v0 by d. And the second differentiation with respect to y will be 0 because there is no y term here. And third differentiation of v with respect to z will be 0 because there is no z term here. Then we will get electric field vector as minus v0 by d, and the direction vector ax should be written as it is. The unit for electric field intensity is volts per meter. So this is the expression for electric field intensity in the region between two plates of the capacitor. Next, we should estimate what is the flux density. We know flux density is epsilon times E, where epsilon is epsilon naught multiplied with epsilon R. So taking this vector and multiplying with epsilon naught epsilon R will give the flux density, whose unit is coulomb per meter squared. Next, we have to find what is the charge enclosed from Gauss law. From Gauss law, this flux density integrated over the closed surface will give the total charge enclosed. Thereby, we can take this d vector, do the surface integration to get the charge stored on each of the plates of the capacitor. So this substitution can be done over here, and the surface integration has to be taken. We can take out the constants outside the integration. The constants are epsilon naught, epsilon r, v naught, and d. And surface integration ds usually gives the surface area of the region. So now when we look at the parallel plate capacitor, we have the two parallel plates which are rectangular in shape. So the surface area of this particular plate we should write. Since both are symmetrical plates, both have the same surface area, we can write the surface area of the parallel plate, which is rectangular in shape, as the length multiplied with breadth. So L into B of this plate will be the surface area, which has to be replacing the surface integration ds for this case. So when we put that, we will get charge Q as minus epsilon r V naught by D into surface area. So when we look at this Q, which is negative, talks about the plate which is charged to negative, or which is connected to the negative supply potential. And the other plate is connected to the positive potential. So equal and opposite charge will be stored on this plate. So for the first plate, if the charge storage is negative, the same magnitude will be there, and the polarity is positive for the second plate. So equal amount of charges are stored in the parallel plates, where one is negative, another is positive. So we can take this charge and also the difference in potential to get the capacitance of this parallel plate capacitor. We will proceed further now to get the capacitance effect. The charge will have the unit of coulomb. We must write the unit for each and every quantity properly. And in this case, the definition of capacitance is ratio of charge stored in either of the plates to the difference in potential between the two plates. Now we know one plate is charged to 0 potential, another is charged to V naught potential. So V difference can be written as V naught minus 0. That is going to give V naught as the difference in potential, which is the denominator term. The numerator term is just evaluated, which is charge stored in either of the plates. We can take the magnitude of the charge, because one is charged to negative means the same magnitude will be therefore the other positive plate as well. So we can take the magnitude of the charge stored divided by this V difference, will be giving the capacitance of the parallel plate capacitor. In this case, for parallel plate capacitor, capacitance is found to be epsilon naught epsilon r into S, where this S is the area of this rectangular plate and D is the distance of separation between the two plates. And the unit of capacitance is in farads. Here, when you look at the capacitance of a parallel plate capacitor, it depends on the material dielectric constant, that is epsilon r. It depends on the geometry of the capacitor, that is the area of the parallel plate, and also it depends on the distance of separation between the two plates of the capacitor. In a similar way, we can do for the other cases of examples of capacitances for the other coordinate system as well. I hope you have understood the capacitance derivation from the Laplace equation. Thanks for watching the video.